The basis for kinetics is Newton's second law of motion, which, as we know, states that when an unbalanced net force acts on a particle, the particle will accelerate in the direction of the force with a magnitude that is proportional to the force. Keep in mind that the net force on the left side of the equation can be represented as F summation F or F sub r, each of which represents a net force, i.e. the summation of forces. Problems that involve analysis of forces require a free body diagram, FBD, of the particle to be drawn, showing all forces acting on the particle. It is optional to also include a kinetic diagram, which is introduced in this chapter. That kinetic diagram shows the vector ma acting on the particle. So free body diagrams, as you know, are a crucial part of any engineering mechanics class. We really study them in depth, these free body diagrams, in statics, and we're going to draw quite a few of them again for this class, especially in this chapter, chapter 13. The FBD, as you know, shows all the forces acting on the particle, but does not show anything else outside of just that particle and the forces acting on it. So here is a free body diagram of this particle here that's being subjected to forces F1 and F2, representing those forces as vectors. So the net force we can find to be in this direction based on the head to tail method or parallelogram law of vector addition. And what we're saying here is that the FBD is equivalent to, or this scenario is equivalent to, this scenario here, in which we show just the MA vector, which is equal to the net force vector. This diagram here is known as a kinetic diagram. We will now apply this vector equation of motion to a particle using a rectangular coordinate system, an XYZ coordinate system. So here we have an XYZ coordinate system. The blue curve represents the path that the particle is traveling along. Here we have the particle with forces F sub x, F sub y, and F sub z acting on it, and the coordinates of the particle at this instant are x, y, and z. The diagram here shows the forces F sub x, F sub y, and F sub z acting on the particle and therefore represents a free body diagram. Applying the vector equation of motion using Cartesian vector notation, meaning using the unit vectors I hat, j hat, k hat, we have the following. So on the left side, we had the net force. In Cartesian vector notation, that would be summation F sub x times I hat plus summation F sub y times j hat plus summation F sub z times k hat. Then on the right side of the equation of motion, we have the scalar m mass times the acceleration vector, which can be represented in Cartesian vector notation as a sub x I hat plus a sub y j hat plus a sub z k hat. So remember that the I hat, j hat, k hat unit vectors act in specific directions. Each one of those unit vectors has a magnitude of exactly 1. The I hat vector always corresponds to the positive x direction, the j hat to the positive y, and the k hat to the positive z. This vector equation can be separated into 3 independent scalar equations of motion, where summation f sub x equals m a sub x, summation f sub y equals m a sub y, and summation f sub z equals m a sub z. Okay, so this represents the net force in the x direction, net force in the y direction, and net force in the z direction. M, as we know, is the mass of the particle. A sub x, a sub y, and a sub z represent the x, y, and z scalar components of the acceleration of the particle. So these equations can be used to solve problems that involve force, mass, and acceleration using a rectangular coordinate system and XYZ coordinate system. As stated previously, remember that a properly drawn free body diagram must be drawn before applying these equations of motion. We will now apply this vector equation of motion to a particle using a normal tangential coordinate system. A normal tangential coordinate system is often used when a particle moves along a known curved path, such as a circular track. Here, the equation of motion is expressed in terms of components along the tangential t, normal n, and binormal b directions. Note that there is no motion in the binormal direction since the particle is constrained to move along the known path. And recall that this coordinate system is unique because the origin, and therefore the orientation of the axes, constantly changes with the changing motion of the particle, and the origin of those axes is always located at the particle itself. The diagram below shows the net forces in the t, n, and b directions acting on the particle, and therefore represents a free body diagram. Applying the vector equation of motion in terms of the unit vectors along these coordinate axes, we have the following. So on the left here, we have the net force expressed in vector form using those unit vectors in the t, n, and b directions, those summed together. On the right, we have mass times acceleration. which would reduce down to what you see here, these two terms instead of three terms, because as we mentioned, the acceleration in the b or binormal direction is zero because the particle never moves away from the known path shown in blue and therefore never has any actual motion or acceleration in the binormal direction. So those two terms on the right are mass times the a sub t, acceleration in the tangential direction, and mass times a sub n, acceleration in the normal direction. This vector equation can be separated into three independent scalar equations of motion, where we have summation f sub t, the net force in the tangential direction, equals m a sub t. We have summation f sub n, the net force in the normal direction, equals m a sub n, and summation f sub b, the net force in the b binormal direction, equals 0. These equations can be used to solve problems that involve force, mass, and acceleration using a normal tangential coordinate system. As stated previously, please remember that a properly drawn free body diagram must be drawn before applying these equations of motion.